she graduated the Coimbra, Portugal, Coimbra and Portugal, and she got a PhD in the material science and engineering from University of Lisbon, Portugal. And he's head of the group of material structure at the Department of Structure Analysis of Institute of Physics, Czech Academy of Science. And her main topics is the frustrated and the highly correlated electron system. So he's also the member of the magnetic structure analysis of the Commission of Magnetic Structure of the IUCr. And he's a specialist in this field. Thank you.
Thank you for the introduction, and also the organizers for inviting us here for this such nice and rich week in terms of magnetic crystallography. So I work directly with Václav Petříček. He's as Cynthia said, he's the one coding Jana. I do not code, but sometimes we exchange some glance at the lines, the command lines. I kind of stumbled into this group because they needed someone to tell them, okay, from the experimental viewpoint, what is needed, what are the needs of this community of the instrument scientists. So they sent me sometime to ILL, and I brought data, and this is how I end up working with him. So I will just tell you, so many of these things you heard already in a general way from Manu, from Branton, from the theory, or from Juan. But Jana has a specific formalism for the structure factors, especially for modulated structures, and I will present what differentiates this program. So I will show you the formula for magnetic structure factors in Jana, how we do representation analysis later, how Jana handles symmetry, which you heard already from Cynthia for normal crystal structure, standard crystallography. And then I will show you how, what is the flow, how the magnetic part of Jana works. So all the lectures this week have taught you that in your magnetic materials, you have a periodic moment distribution, which is described by a periodic vector function in the three-dimensional space. This, the density of the spins in your material is then described by this Fourier summation of the magnetic structure factors in your structure. So then the magnetic structure factor in Jana, which we use in Jana, is this form here, and is composed, of course, by the contributions of all the magnetic atoms in your structure. And you have derived this expression with Javier early this week. So you have this P at the beginning, which is a factor for unifying scales. Then, of course, the position, the temperature factors of your atoms, and the magnetic moment, and the magnetic form factor. You also have seen these things before. I will just want to remind you of them in a more practical way. So here you have the comparison of the magnetic form factor from X-rays and for neutrons in colors for different oxidation states in manganese. You can see the difference with scattering vector. And then you have here also comparison for neutrons for the manganese and the D elements. you see that the d elements have this extended part, which have to be taken into account in the magnetic form factor, which you input during your refinement. So also you see here what is the main reason why we search for our magnetic scattering at low angles, because this decays very fast with scattering angle. So we have also seen that modulated incommensurate magnetic structures can be described by the superspace approach. So the core of this approach is that the magnetization density is generalized to higher dimensional superspace to recover the lost translation symmetry in the real space. So the magnetic moment is then given by this Fourier series, where you have here the M0. So M0 is your general term, and then you have here these sinus and cosinus amplitudes. Then the kinematic theory of diffraction tells you that you'll have satellite reflections at certain positions, which also depend on your k-vector. Javier has also told you that the magnetic diffraction intensity is, as this expression here, when you work with the non-polarized neutron beams. So what you have here is that the intensity, only the magnetic part is, so you have these correction terms, so Lorentz, absorption, extinction, and then you have this part that tells you how the magnetic diffraction occurs, so this is the geometric part. For such beam, the nuclear and the magnetic intensities are just independently, so the programs we have for treating data can use this feature to choose if you want to combine these data or if you want to treat them separate. In Jana, we use the combined, we use the nuclear and the magnetic data combined, and we use the nuclear reflections for scaling of the magnetic moment in your refinements. So now that you know the equations about diffraction, you know where to look for your magnetic diffraction satellites or intensity. So for the simple k vectors, you'll have the magnetic diffraction over the nuclear intensity. For the antiferromagnets, you will have the satellites located in reciprocal space positions given by the coordinates of your propagation vector, magnetic propagation vector. And then for the incommensurately modulated structures, you will also have this the same, so that the satellite positions will be given by the k vector, but you can have you will have k and minus k there on the right side. You will have lines or systems of satellites if you have harmonics of your propagation vector, or you'll have a system of satellite reflections if you have more than one k vector. So around your reciprocal point, you'll have nice patterns of made by new magnetic satellites. So for instance, here you have this compound is in the paramagnetic phase, so you have the nuclear reflections. This is Laue diffraction, it's not a reconstruction of the reciprocal space. This was from Cyclops at ILL. So when you lower the temperature, you'll see the satellite reflections appearing for this incommensurate phase. You see that they are in some, they are not in between the main reflections. Then this other one, which also, so the first one is a cycloid, this one is a spin wave, and then you have the commensurate magnetic structure at the lower temperature. So the commensurate structures are usually less energetic, and it is normal that you have such structures at low temperatures as the ground state of your system. So this one is, so here in this side you see the paramagnetic pattern, so the nuclear pattern of an hexagonal structure. And then when you lower the temperature to reach the antiferromagnetic state, you see what happens here. So this is 2K incommensurate structures, vectors, and you see the system of satellites around your nuclear reflection. So you have also seen this week that there are two main approaches to describe magnetic structures. You have learned about magnetic symmetry. You have learned about irreducible representations. You have seen that both methods have weaknesses and strengths. And Manu, Brandon, and Juan have also explained that a magnetic space group is basically a usual crystallographic space group extended to include the spin by a specific operation which you have seen. It's called time reversal. So Manu has clearly stressed out that the space group contains all the constraints for the structure, not only positions and atomic parameters, but also the magnetic configuration, and that representation analysis uses group theory to find the possible active irreps and its basis vectors, which then translate to as the modes allowed for your spin in your structure. You have seen that representation analysis sometimes can be, it is a difficult problem mathematically, but we have tools. We have tools to tackle this problem. You have seen Sarah and basis reps and such. And we also have space group and super space group specialists, super space group libraries, which help us with the magnetic space group formalism. And even better, some years ago, Branton and colleagues have found a combined approach of these two methods, which consists in calculating the magnetic space groups or super space groups for the set of active irreps for a given paramagnetic space group and your magnetic propagation vector. So these are called the isotropy subgroups of an irrep, and it's a very robust and efficient method. You have also seen that if we have one-dimensional irreps, we have a unique correspondence between the irrep and the calculated magnetic space group. But when the irrep is multidimensional, the situation is not so simple because it depends on the combinations of the basis vectors. So you have heard of order parameter directions. So in Jana, representation analysis goes like this. So from your paramagnetic space group and the propagation vector, the star of your vector is generated. Then the active K vectors in this star are selected, which means that then you have your irreps defined. Then the isotropy subgroup order parameter directions are searched, and this brings us to the 3 plus D dimensional magnetic superspace groups for incommensurate magnetic structures and magnetic space groups for other simpler structures. In these space groups, superspace groups or space groups anyway, the magnetic structures are given are the configurations that are symmetry, the symmetry allowed directions for your moments. So in Jana, at the beginning, after you decide that you want to treat a magnetic structure, you have this drop-down menu where you see you define your IREP type, or which means you input your propagation vector. You can see that also there are these two notations, so Kovalev and CDML, which you have seen also these days. So later in Jana, you'll see that there are particular IREPs for, so you'll have for this paramagnetic space group and this propagation vector, you see the representation, dimension, and the calculated space group. So if you go for details, you'll find the symmetry operators and other details. If you do display representations there, what you see, you'll find a long file. You'll find a long file with all data used to define the active IREPs in your structure and the listing of the symmetry operators of the groups, the irreducible representation matrices and characters and all this, as you find in BASIREPs, Bilbao server, or also in isotropy suite programs. So this is only part, so there's more. So then, if you have been paying attention to the lectures this week, you will tell me, but wait, you said that if your IREP is not the dimension 1, there should be more groups. So yes, so these are only the kernel symmetries of the IREP. So these are the ones for which the magnetic space group is kept in any general direction of the IREP space. You see that. Then in the following window, we add the epikernel, the IREP epikernel space groups. So you see that, for instance, for any of these representations, you have here at least 3 magnetic space groups. And you see also there, it's the column with the order parameter direction, in which you see the general direction, so the kernel groups, which you saw first, and then the 4 epikernels. So the same is valid in superspace, of course. The windows are just the same, calculations are made the same. Just in general, we do present instead of the full dimension of the IREP, we present the dimension of the little group. The same information you can see. So, and there are more details. So these windows have always buttons with in which you can display more informative details if you want to check them. So for magnetic diffraction, the magnetic diffraction, of course, follows the Laue symmetry, and because we have this prime in the space groups, but you cannot see the influence of this sign directly in your pattern. And then the diffraction symmetry cannot be used to find the magnetic space group, because so when you have single crystals, you create immediately equally populated domains. Because you decrease symmetry, you create these domains. And for powder data, these reflections are completely overlapped. So as Cynthia said, superspace approach is implemented in Jana for the three dimensions. And everything she said about this is valid also for the magnetic part. I just wanted to stress this out. So for the magnetic moments, the symmetry restrictions are, all symmetry restrictions are derived from the list of magnetic space group operators and the atomic positions. And these symmetry detected relations that Jana finds generates are activated by default also for the magnetic moments. They list the restrictions and generate the commands that you need to use during the refinement. This can be, of course, you can disable these, but then you are on your own. You have to input all the constraints that your structure needs in order for the refinements to proceed. So these symmetry restrictions you can see for any atom in the edit part of Jana. In this you have here this number is the listing of atoms, so you can access the listing of atoms in your structure. And in this edit part, you can see the restrictions one by one. So you'll see that if you click here in show symmetry restrictions, what you see is this one. So all Y components of this modulation are blocked, are non-allowed by symmetry, because you see immediately that this atom is at a special position, so there's no magnetic moment allowed in this direction. And the same for non-modulated part. But also, if you want to see all these restrictions at once for all atoms and also other refinement restrictions, you just open the refinement file in this tree of commands, and they are all listed there for all atoms. So in addition, we have this tab, on refinement commands, in which the user has the possibility of controlling the structure. So there's these restrictions, the way how to restrict angles, distances, and magnetic moments, also the refinement and such. So for instance, in this magnetic moment restraints, you have these commands here, which allow you to fix the magnetic moment to a specific value, or to group atoms and to restrain them to have the same magnitude for the magnetic moment, or to only apply rotation when you have some modulation. So the magnetic structures can be constrained by these specific commands. As Cynthia said, there's these restrictions, equations, and commands. Restrictions are used to make generally, but this can be made differently. Restrictions are made to make identical parameters for a group of atoms in the structure. Also, linear equations can be used with these variable names of parameters in Jana. So this is like program language style equations, nothing really difficult. and keep comments as also a comment for magnetic atoms, which is here. And in this case, this was made to keep this. So these 4 manganese atoms are grouped together, and this is to keep their a perfect cycloidal modulation for all of them. This is the result. So to refine magnetic structures, of course, Jana refines all the usual structure parameters. So the scale, extinction, ADPs, the magnetic moments for the allowed components, and also for the magnetic modulated ones, commensurate, incommensurate. Also, Jana can perform a combined refinement of magnetic moments for the case when the crystal structure is already modulated. So again, the reflection conditions also for the magnetic moments are derived automatically in Jana from the magnetic symmetry operators and the position of the magnetic atom in the unit cell. As I said, the nuclear and magnetic contribution are usually not separated in Jana, they are used together. We create first a representation, what we call a parent structure, in which you have your crystal structure information and the magnetic propagation vector input. Then we perform a representation analysis, calculating the isotropy subgroups of the possible active reps in your structure. And for graphic visualization, you have seen that we have now Jana Draw, which is our internal interface, which allows you to follow the structure even during the refinement. You'll see the structure change immediately, so powders or non-powders. And then Jana also for magnetic moments, for magnetic structures, usually we call Vesta, because diamond, you have no vectors. Or we can, Jana produces CIF files or MCIF files for any program which uses them, like a JMOL. So how this works? Okay, there's no mouse. So in this orange part, you first input the CIF file with your paramagnetic structure here in green. Then you define which atoms in this cell, in this unit cell, are the magnetic atoms. You choose which magnetic form factors you need to work with, and you input your propagation vector. Then you do you import your data file from your experiment. Then if you have powder data, Jana will perform Lebel and Rietveld, so profile and structure refinement. If you have single crystal data, Jana will immediately calculate the isotropy subgroups. It performs in the representation analysis step in the middle, and then you can even from this step you can already connect to IsoDistort or Bilbao server to have representation analysis from them, or you can start the process of selection and testing of your space groups against your data. Once you have the final model, you have the way how to draw the structure, or in the end also you have the production of CIF files. So this is a typical window of Jana where you will choose how to start your magnetic structure. Usually we start by with the CIF file of the crystal structure. Then here is the window where to define. On top you will define the number of your reps you have and the magnetic propagation vector of your structure. In the middle part you choose which atoms are the magnetic ones, and then you have this in the lower part you choose the form of your magnetic form factor for the atoms you have. Then you enter some cycle in which you'll perform Lebel. So Lebel refinement, you see this is a magnetic structure because you have nuclear, and so nuclear is green, this pink is for magnetic ones. You can keep this window open and check all the time how the refinement goes. And then you can zoom, you can see what is going on with your magnetic reflections at a certain point. Then now we have also introduced the possibility of search for the propagation, the magnetic propagation vector when you have powder data. This is accessible. So this function, you can use it when you have your parents, when you are in the stage with your parent structure yet. So you edit your profile, and then you change your propagation vector in this menu here. And then in this tree, you will have this option, random search for modulation vector. And then this will perform a normal. You'll see these windows. You can choose how to search for it, and you'll see it as there will be some factor to tell you if this is converging, this procedure is converging or not. So representation analysis in Jana is limited for now. For more than one modulation vector, we rely on isodistort, which can be called directly from Jana, and then the selected models are displayed, and we can refine them. So Jana can connect to isodistort directly from the tools. So if you need something at the beginning, or Jana can prepare CIF files to export to isodistort and then import the resulting IMCIF files to test against your data. So we will not show this here today, but there is, in the cookbook there is an example for the communication between Jana and isodistort. So you see, you know now, because Branton yesterday beautifully taught us how to do it. So it's just the normal procedure, but then here you save CIF files that Jana will read in the end. Branton says that he does not call them MCIFs, so Jana also does not call them anything, so we just import them and that's it, with all the information inside. We just have specifically MCIF files for Bilbao server, because Bilbao server uses shorter versions of these files, so there's no need for so much information. So we have a specific format for this. So then you'll see Jana inputs the zip files from ISO-distort, and in this window you can choose which models you want to test for your data. And if Jana performs a representation analysis, this is how it looks like. You have you have the first column with the representation, its dimension, the calculated space group, in this case Shubnikov space group, and then you have other parameters for the structure. In details, you have these details that I showed you before about the representation, the rep, and the operators of the group. So usually here, as I said before, this is the window with the groups only for the rep kernel symmetries, and then in the following window, you'll find a more extended list with all the space groups, kernels and epikernels, grouped by decreasing symmetry. And usually this group is kept as a unity, and if you press there next, then you have access to information from each one of these groups. For instance, here you can see for this second space group with prime M, prime C, this is hexagonal structure, you can see that there are three magnetic atoms in this structure. The moments are aligned along the C-axis, so this group only allows moments aligned along the C-axis, and that this is a ferromagnetic structure. You have a global moment, which is non-zero. The same, of course, for the superspace groups. The only difference is that now you will have the Fourier components for your wave. So it just works just the same. So if for any of these space groups in the last window, if you perform start graphic simulation, Jana will display, so what is your structure? Where you can see visually where the moments are. If you start this profile simulation for your powders, you'll see what are for each of the reflections. So again, magenta are the magnetic reflections positions, and the green is the nuclear ones. You'll see if you click over the position, you'll see, for instance, information in what is the reflection, so the indexes, the position, and if there is any structure factor calculated for it. So in this case, this does not allow any magnetism in these positions. So the structure factor is zero. To understand, to describe your structures, you can, or even to present your results, you can now use Jana Draw. So Jana Draw, this is for one of the structures of a famous one in this workshop. So this is the double helical dysprosium manganese 6 germanium 6. I think this is a very useful tool because modulated structures especially are very difficult to understand, and you can just play around with them here you don't need to go to some other program to have immediate drawings of what is doing. And you can save movies of these. So group-subgroup transformation for the magnetic space groups is also available in Jana. You'll see this afternoon in one of your examples. what you do, as Cynthia said, you just choose from the list of operators of the space group you are working now. So your father or mother group, and you choose which of the operators will be the generators of your lower space group. So then you just ask Jana to complete subgroup, or you can complete it by yourself. And so you'll see in the end that you have the child group and your own group, the parent, not the parent, the father, let's say. Then Jana will tell you that you can choose the coset representatives that lectures told you before about. So you can choose it yourself, or so the composition, or you can let Jana do it for you. And then that's it. You just have a new subgroup. Jana will ask you if you want to work in this subgroup or not. And this is all the procedure also for the magnetic moments. So if you import your mode analysis, for instance, from ISODistort, Jana can also do a little bit what ISOVis does. So you have these bars there in which you can play with the modes. So that you see which modes are active. You can switch them on and off like ISOVis does. There is an option which sometimes is very useful to describe, to understand the directions of your magnetic moments, which is refinement in spherical coordinates. Then what you'll see is the change in your parameters from XYZ directions to the amplitude and 2 angles for your magnetic moment. But in this option, Jana does not apply any symmetry restrictions. So this is, you have to think how to do it and input the symmetry restrictions by yourself. There's also, if you, in the end of the example, the last example for this afternoon, there is also, you can play a little bit around with this option. Then there is graph T. Cynthia showed the concept of graph T, so that you can choose what modulation variable you want to see. In the case of the magnetic moments, you can see the components or the amplitude as a function of this phase part. So this what you see here is the plot of the amplitude of 3 different magnetic moments in a structure for one period of your modulation. So during one period of your modulation, you can see how the moment behaves in your structure and what is the relation between them. In the end, you will well, this is more enforced for the crystal structures, but now we also would like to enforce it a little bit more for the magnetic structures. So you can produce magnetic CIF files. There's different formats in Jana for the CIF files. What we need only is this CIF make. So CIF make will produce a complete CIF with the structural and the structural and magnetic information. And then we have this specific MC4 Bilbao server, which I told you is a shorter version with only the main information for the Bilbao server programs to work with it, with the magnetic structure. So you would like this file for reporting or for publication of your information. So even better is if when you publish, you describe, you send to this publication a good description of your structure, including your magnetic space group or superspace group in the publication. It does not need to be in the main part, but it can be supplemental material or something like this. So that someone who needs can at least reconstruct your magnetic structure without having to figure out if the figure A corresponds to IREP M or IREP X or whatever group. So there's, Manu will talk more about this tomorrow, but there's a very nice guidelines now published for the publication of magnetic structures in this paper here. Also, if you want to know more details on the magnetic option of Jana, we also published this paper. There's a lot of details, a little bit of the thinking behind this option from Jana. For this afternoon, I hope you all have the newest version installed, not the one online, because the one online is for general purposes, but you have a special one that Václav just rearranged for this workshop. I think we all have been using it, but it just does not want to go through the trouble of changing it online for everybody so far. He just thinks it's a few changes. That's just this. There's not... and that you also connected Vesta with Jana, but we will then go through this. Also, there's this cookbook, as Cynthia said, and there's now, I think, 12 examples dedicated to magnetic structures. So from scratch, from a simple commensurate magnetic structure to incommensurate magnetic structures. And if you want to look for the numbers, the reference of the magnetic examples is this 12. So thank you. If you have questions, just we are around.
Thank you. Margarida, the previous version of Jana had the feature that you could refine the modes within a given magnetic space. No, about an ordinary space group. I mean, and the point is that there was, you know, IsoDistort can produce this a PCR file, and Jana, the other version, was able to read these PCR files. Mm-hmm. And I asked Václav, and he said that the new version can do it also for ordinary structural distortions and for magnetic arrangements also. And I think you show something related with this, because you show this.
Yes, I showed where you can play with the modes, but you
yes.
can also refine.
You can also refine
Yes,
these modes.
this new feature with the commands like isovis.
But how can you arrive to this mode decomposition within the magnetic space group?
No, we import it from Branton.
Yes, but in which format? I mean, you read the PCR file, or what do you read? Or
No, the distortion. The CIF or the distortion file, I think. The CIF.
Only the CIF. Okay. But, okay. That's,
Good afternoon, everybody. So now the afternoon lecture will start by the Margarida Henriques. Okay.
So if you download the PDF or Word files with the examples, there are 2 of them. If you had some difficulties, you can still ask us, because we have the programs in some USB keys here. So if someone does not have Jana or anything, or if you have had troubles, just let us know. You also are supposed to connect Jana with Vesta. So there's a specific place in Jana where you should do this. When you open the program, you have here these settings and then programs, where you should put the address of the executable file from Vesta or whatever program. So here, you should tell Jana where Vesta is. This is not very important for the first example we're gonna work with, but it will be for the second one, okay? Okay, so the first example we're gonna work, we're gonna copy a little bit the working logics of Branton yesterday. So the first example, I will go here slowly and will guide you through menus and all things you need in Jana. And then in the second, I would also suggest that you group yourselves 2 by 2, and one read and the other follow the instructions in Jana. So it will be easier and you'll learn a lot. And we'll be here also to help you. And if there is some specific question, problem, whatever, you just call us like yesterday. Okay? So let's start. This example is the 12.9. It's a nickel tellurium oxide. This is a simple antiferromagnetic structure. The data is a single crystal data collected at Oak Ridge National Laboratory. But we don't have the data from the instrument. We have the data file from FullProf because we wanted to to compare the 2 treatments, and also they had some problem with data reduction. So this is why we have the FullProf file instead of the instrument data file. So the propagation vector is 0 in this case, and we will work on extinction correction for single crystal data models, and also on lambda 2 correction, because all the instruments, they produce higher harmonics of the main neutron wave, and sometimes they cannot filter it in anyhow. So we can correct for it in Jana, okay? So if you open Jana, If you open Jana and you go to this main menu, you have here on the upper left corner structure. To start a new one, you press new, and then you just choose where you'd like to work. When working with Jana, it's not a good idea to work in any cloud or in flash disks, or even sometimes in the desktop is not a good idea, because Jana generates a lot of files that you don't even see, that they are hidden, and they are for communication during the refinements. And this means that if the files have to travel somewhere else, there's no time for a response, like a useful time for response, and then the program will crash. So we're gonna call it nickel something, just the root, nickel telluride, tellurium oxide. You do open, and then we're gonna start our magnetic structure by defining the parent structure. So we're gonna tell the program what is the crystal structure of your crystal, and Jana knows that the model will come from a CIF file. So CIF and then next, and you just choose the nuclear CIF that you have here. Okay. And here you will define your propagation vector and the form factors. So we have k equal to 0, which is already here by default. And then you have here you can choose from this listing of atoms which is the magnetic one. So nickel is a magnetic atom, so we say nickel use as a magnetic atom. You can choose in this drop-down menu what is the oxidation state for your ion, because these oxidation states also change the form factor. So nickel 2+, and we keep this J0 because it's the simplest expression for the magnetic form factor. All these values, we just choose them, but they are tabulated. They were determined by people at the Neutron sources, and they are tabulated in the international tables. So then the program tells you, okay, we know what is your crystal structure, and we know what is your propagation vector. Now, where is your data? Now the data is from single crystal, already corrected for Lorentz polarization and absorption. You just go next. We have a full profile, so here you see the different types of files Jana can import. But don't worry if you don't have any of these formats, because then here you have these fields in which you have general file on factor, structure factors or on intensity that you can import. If you click here, you'll have this Fortran type command for the format, and then Jana will read whatever format you tell it to read. So in this case, we have a full profile, and it is this int file. Next. Oh. Because the name is not complete. So the file has this other portion, nuc 4k, which was not the default one. So next. Here you see what is reading from your CIF file, so that You have the cell parameters. You have that this data is neutron data, and the wavelength, because I already worked with this example, so it is already here by default, but you should put it yourself. So the wavelength you use during your experiment. Temperature is 4K, but you can change it to 4K, but this is only when you need to correct something which is a thermal parameter. So if you don't need to correct the parameters, it does not matter. Just temperature is an indication. And also it's good because this will be written to the file. If you have a lot of files, this will help you to distinguish between them. So next. So this is the cell parameters. They are okay. So now Jana has this information which tells you if the importing of the reflections went well or not. And that's it. Now the import part is complete. In here it would be the step. So here we'll finish, but this is the step where you can import more data files. So here, instead of going forward with this one, you'll say re-import or import new. If you have like a bank files, this is the place where to add them. So this is our file. We say OK. The parent structure is now complete. You have your reflection file. So now Jana will perform the calculation of the isotropy subgroups. And if you look here on the right side, you all the time you know in which step of the process you're going. So it's okay. So again, here you have the kernel symmetry. So Jana calculated just the Shubnikov space groups consistent with your paramagnetic space group and the zero propagation vector. These are the general direction space groups. So this the rep kernel subgroups. And here you have all of them. And then you have these blocks. In this case, you only have one block because you only have this orthorhombic family. But in other cases, you have lower symmetry. So Jana groups this by symmetry. So if you have orthorhombic, monoclinic, triclinic, you'll see them just by this order. And if this, you see all the block is blue, it means that when you press next, this will bring all these PNMA groups for further testing. So here we know already that where is the solution. So for each one of these groups, as I said, you have here what is the moment. So this is antiferromagnetic configuration with moments in all the space directions, and this probably will be different. So you have here a ferromagnet, another ferromagnet. So you see another antiferromagnet. So this is a sort of a filter, because in the beginning you already know if your structure is ferromagnetic or antiferromagnetic. So which means that here you can already exclude some of these space groups. So we will use PNMA. And here you press continue with the selected Shubnikov group. So then there is this pop-up window, and you can save this structure with the default name or something else if it is confusing for you. Just you can, of course, this is personal matter. So save, and then it will open this new window, so that in the background here you have access all the time to the parent. So if there is some problem with the groups you chose, you can go back and perform a representation analysis. You will see that, for instance, here you have these tools for magnetic structures, and in this tab you can also connect immediately to IsoDistort. So if you see something in your data that needs further checking or further analysis, you can go back. Okay, so this is the first group, and because FullProf uses average data, non-average data, and Jana usually performs averaging of all sets of data, what we will do, we will create a new reflection file. So here in this tree, you just click a reflection file and create refinement reflection file. It will just open windows with the conditions for what you want for this file, but you can just continue because we usually accept the 3 sigma deviation. And here on top, you just click use non-average data. Next, and finish, and you have a new file. And then in this tree, you have here refinement and refinement comments. As Cynthia said before, you can have access to all these, to the most of these 3 comments in this on these menus, but for beginners I recommend to open the panels in the tree. So here we have a lot of things. So the refinement, how the refinement will work. This is for the listing. So what you want in your output. If you want to see a lot of reflections, if you want to see less reflections, the most important ones, but an important tab is these restraints and constraints. So I told you that Jana creates automatically the restraints for the moments. What you see here is that you have ADPs restricted already. If you click over this, these restrict 1, 2. So this instruction means that ADPs are fixed for all atoms. And also in fixed comments, you'll see, oops, too fast. You also see that the coordinates are fixed. So then we go back to the basic window. Usually in magnetic structures we use this 100 cycles and damping factor, which is how much you allow the moment to fluctuate, or how fast you allow you want your refinement to converge. And then you have here the automatic refinement keys, this block here on the left, And if you have very good data, which is not the case for magnetic structures most often in terms of, they are not as good as X-rays. If you have a good set of data, very nice, you can refine in F squared, like with X-rays, but usually I do not refine magnetic data in F squared, but on F. So, because F squared will propagate errors, so any error you have in your refinement will propagate fast. Any error in your structure will also propagate faster. So let's refine on F. So you just disable refinement on F squared. And OK. Yes, and start. And this will start your refinement. You'll see here the window with the R factors for the nuclear contribution and from the magnetic contribution. This error, this serious warning. So let's refine again. So this error you see here, and people usually are scared when refinements say there is a serious warning. This serious warning is about the ADP parameters because we collect the neutron data at very low temperature, and in this case there's not many thermal excitations, right? So if we need, we will fix this later. This is also indication of sometimes it's indication that your space group is not correct. So we're going to now I will tell you how to release, how to refine the coordinates. So we go to, so here in run refinement, you cannot see. Okay, so in this tree, if you click again refinement commands, and you go to the tab restraints and constraints, you have here this fixed commands again. You just select the line that fixes the commands, and you just press here on that side disable, okay, on the right side disable, and that's it. This condition is not enabled anymore. So okay, yes, and start. And here you see that the refinement is a little bit better. But let's see what is going on with the reflections. So also in this command tree, you go back to reflection file option. And then there's this line, manual culling. And here you see the reflections. And this is the weighted, observed minus calculated from the refinement. If you choose observed versus calculated, so the last option here, you should see this image, right? So you can see here that the observed intensity of the strong reflections is a little bit wrong. So this is a sign that there is extinction in your sample. So let's correct this. So if you go down again in the tree, and you open the part of edit structure parameters, you'll see the last line is edit extinction parameters. Just click over it, And here it appears the models that Jana can correct. So we're going to choose an isotropic model. And then you have this type 1 and type 2. So type 1 is the mosaicity of your sample. And the type 2 is the relationship between particle size and the wavelength you are using. So all these relationships are given by distributions. And we're going to try like the different models. So we're going to choose here type 1 and the Lorentzian. Okay. Yes. And if you click here in this first button on top of these shortcuts, if you click over it, you'll see what these icons mean. So the first one is run refinement. So if you click over run refinement, this first one here in blue, you just see what the extinction correction is doing to your data. So what you see is that like the refinement factors are now half of what were before, and that the strong reflections have some reasonable intensity now. So for this data file, as I said, there is an important contribution from this lambda to harmonic during the experiment. So we need to correct this. So if you go to refinement comments, again, in the basic tab, you'll see here on the right side, correct for lambda 2 effect, the first option. Okay. Here we're just going to say yes and start because we're going to do some modifications before running we're going to modify these parameters somewhere else before we start the refinement. So here you say yes. And then here in edit structure parameters, you have here edit scale factors. And the variable that will be refined to correct this lambda 2 effect is this one, sk lamb over 2. So you just click over it. Okay. Yes. And then you press again run refinement on the left corner. So this result, you see how good the R factors are now. This result shows how important is the extinction correction to reach good models in your data. So let's now try another model just for the as an academic exercise, but nevertheless in real life you need to try. So edit extinction parameters, and now we'll try the Gaussian type. Okay. Yes. And refine. You just need to refine. It will complain that the changes are too large, but it will go nevertheless. So if you look, you can already see what is happening with the you can already see what's happening with the reflections here, that now they are in a worse position than for the previous model. So this model is not so good as the previous one. So let's try the type 2. Okay. Yes, you want to rewrite the files and you want to refine again. So it's not a bad model, but we have better. So we're going to go back. We'll go back to our type 1 Lorentzian here. So type 1 Lorentzian model. And because the samples, these default values that you find most often in Jana, they were put here for X-rays. And because the samples for neutrons are usually considerably larger, we're going to increase this, the size of the sample here in a radius for 0.5. So everybody's following, right? It's not hard. It's all good? So we have our model. Back again. We can check. So we can check what are the values for the moment. If you go here in refinement, you have here view refinement listing. In refinement listing, there's all parameters from the refinement file. This is very small because my Václav is like meter screen, and all the fonts are not very good for small computers. So here on top, if you say go to, you can choose which part of the file you want to see, or you can just scroll down. But sometimes this can be very big files. So if you here go to interpretation of magnetic parameters, it will bring you to the bottom of the file, and you have the MXYZ. I don't know why there is a negative one. But sometimes this happens because Jana starts from random numbers, and you have to play around until it gets it right. So what I'm going to do, because it's this minus, I will close this, and I will go edit my atoms. I will click over nickel. This is not in the example. I'm just going to change it by hand so that we all have the correct. Someone else says negative numbers. Because you can either have all positive or all negative, not half middle components with the negative and part mixed. You cannot have mixed. But anyway, so here I will just change it to some positive value. I will say OK, because I know this should work. Yes, and I will refine just once. So you see, even changing the sign does not change the refinement. So now we will draw this structure. So if you just close your manual culling window, you'll come to this one, and here you can change, you have this basic window, which is this black one, and here you have different things. So this one is for powders, so that you can see the profile, but because we are dealing with single crystal, it's not active. So if you change to this icon here, with this benzene ring, this is the access to Jana Draw. So in Jana Draw, here down, this is very much inspired in diamond command. So if you are familiar with diamond, this will not be complicated. And here down you have this fill unit cell. And here it is. So mine is already complete. Probably yours is not. I don't like the bonds, so I will go to this small icon there close to the unit cell, and I will say I don't want to see any bonds, and this is my magnetic structure. If yours is not okay, you can, for instance, center it here. You can choose view along A, B, or C here, anything. To change for you there, to change the background, the black background, you have here options. And in these options, you can change here what kind of background you'd like. So white, light blue. We have this light blue because we have one daltonic colleague, so he does not like the black, but he does not like the white either. And white. Okay? So then you refined your structure, you have your model, you'll probably have some more other macroscopic properties like magnetization, specific heat, or whatever you measure, optical properties. Then you would like to produce a CIF file. So the CIF file, if you push the command tree down, you have here CIF utilities, and you just say CIF make. If you want to, so CIF make will make a normal CIF that contains crystallographic and magnetic information, so a complete CIF file. So if you press CIF make, it will ask you what name you'd like, and it will put into the directory you are working your CIFs. You press save, and now you have the possibility of choose which information you want to input inside. So Jana creates all these files that Cynthia told you about. So here you can say, okay, I want only to send the atomic parameters, or I want to send also the reflections. So in general, or you can say, I don't want to include anything. So I usually include all files. And because those of you who are used to ordinary crystal structures, you know that there's a step before publication in which you have to go through checked CIF. So for magnetic structures, we don't do this. So we say no. And that's it. It's as simple as this. If you want something to be checked in Bilbao server, Jana produces a shorter version of this file, which includes mostly symmetry group operators and magnetic information for the tools of Bilbao server. And it's just this one. And save, and that's it. It just says it has been created. So it was as simple as this. I hope you all could follow. And now the other example is a little bit more complicated because it's a modulated magnetic structure. The structure itself is complicated, but because of the symmetry, the handling of it is not that complicated. So There's no multi-K or anything like this. So we'll be here. If some specific point requires some explanation, just please let me know. I will try to explain to everybody, but I would suggest you work in pairs or some groups, and we will help you. Okay? Thank you.
Maybe now, in the small groups, one person opens the PDF file, and then the second person runs the example 07, right?
Yes, I
Yes.
forgot to say.
So in the folder that you got online, that you downloaded, we have two examples, the 09 and 07. So Margarida did with you 09. Now you open the folder 07. You have there the PDF and the data to run the example.
Yes, and the equations that you'll need to use in order to compose all the restraints for the magnetic moment if you get to the spherical coordinates refinement.
Does anybody have a problem there? Everybody has the PDF in Jana installed? Okay, good. So you can start then. The PDF has step by step what you should do for the example, and also some explanations in between. The blue parts are where you have the text in blue. It's where you should click. And then in black, you have some comments or instructions that Jana will be showing. Yeah, so you can start, and we'll be here around to help if somebody needs help. Yeah.
I just want to add something before. I think it is here. So if you get lost somewhere, because there will be some quite an exercise with the group subgroup transformation. You can go all time around, and you just close your windows, and you have here tools in the parent window. So before the main window that will appear to you, you have here tools for magnetic structures. And in the tools for magnetic structures is the representation analysis. So you can restart without opening a new structure. So without importing files, without defining propagation vectors, etc. So in your parent window, just in your menu, in your tree, you have the representation analysis if you need to see this window by some reason, because at a certain point this will be a lot of windows, and I know it is easy to get lost, okay? But you can also call me anywhere, right? Also case search. I told you about case search. So if you, in the parent structure, if you have your powder profile, you have here a random search for the modulation vector. You just, here we don't need it. Here we don't need this one, but you can just run it, okay?